start now. We're very pleased to have Andrei Beloborodov, who's visiting us from Columbia University. Andrei is a former citizen, so we're happy to have him back here. Andrei finished his PhD in '95 from the Radiative Physical Institute in Moscow, and then he went on to do some postdoc positions in Stockholm University, Stockholm Observatory rather, and then at CITA. And then he ended up at the Columbia University, where he's now a senior faculty member. Andrei is very well respected for his work on gamma ray bursts and Magnetars, and today he's going to tell us something about neutron stars. Andrei.
Okay, thank you. You have a pointer, or where is it? Stay. Oh, okay. Thank you. Okay, so my plan is to give you some introduction to what I think exciting have been happening in the past few years in this field. Because I understand many of you actually don't work. When I was in high energy astrophysics, I hope you follow I think you had a few visitors last semester who spoke about pulsars. And Yuri was here.
Yeah, he was here, yes.
And there was another one? No? Anyway, so I'll give you a very brief introduction. And again, my plan is to talk about a few types of neutron stars. We'll see how well, if I can do this. There's 3 parts in 1 hour or 50 minutes. To remind you, neutron stars are dead remnants of stellar evolution. Basically, compact object made mostly of neutrons, size of 10 kilometers, rotating fast, having huge magnetic field normally. These are the places of the strongest magnetic field in the universe. In hydrostatic equilibrium, like any star. It's supposed to be dead in the first approximation because it's a remnant of a dead star. And the first thing you want to learn about neutron stars when you take whatever 101 courses in astronomy, that they are actually extremely powerful. And this is one classical example, the Crab Nebula, where we see the entire mission of the Crab Nebula powered by the activity of the neutron star. As you know, this is one of the beautiful discoveries in astrophysics a long time ago, that the spin-down power of the central neutron star matches the emission that we see from the nebula. So this is powered by some form of wind from the center. And the remnant is sitting right there. And as you can see, the neutron star, you can see the same in X-rays. Basically this part here, in Chandra image, where you can sort of see the structure of this wind. It has torus plus jet-like structure. So there's a huge luminosity coming out from the neutron star, so it's not really dead in that sense. And the source of energy here, in this case, is just a rotation, kinetic energy of rotating a compact object. It has a period of 33 milliseconds, so it's a lot of kinetic energy in rotation. If you look at possible sources of power for neutron stars, what do you get? Well, you have this kinetic energy of rotation-powered pulsars, what we call. You have a lot of magnetic energy stored in the star, and some objects predominantly powered by this by dissipation of magnetic field energy, which is called magnetars. You can also have accretion in the binary system, and then you are powered by accretion energy. Stuff is falling into the gravitational potential, heated up and emitting X-rays. And also you have another 4th source of energy, which I'm not going to talk about, but there is an interesting subclass of neutron stars which are just cooling passively, sitting after the supernova explosion at the center and emitting quasi-thermal radiation from the surface. But this heat source goes down with time, of course, but there's a lot of it initially after the birth of the star. So I'll try to address at least first 2, recent developments, and then maybe I will talk about the exciting discovery, I hope you've heard about it already, of an ultra-luminous X-ray pulsar in M82. So rotation-powered pulsars. This is actually a fascinating problem. Okay, I think it's a villa. Slow down a little bit. So that there's a pulse of pulsating source, in this case with two peaks. They're typically discovered as radio sources. They have range of periods from milliseconds to seconds. Before recently, they were discovered as radio sources. With the launch of Fermi, we started to discover pulsars also in gamma rays. Just in blind gamma ray searches, boom, you have a pulsating gamma ray source. And in some cases, you can go after it in radio, you can discover also it's a radio pulsar. This is actually outdated. There are many more now, I think 150 or something. Okay, so one surprising thing about these objects that they do emit a lot of energy in gamma rays. Actually, in some cases, a large fraction of the total power that comes from the star in terms of radiation, not just electromagnetic wind radiation, is emitted in the gamma ray band. And how it actually happens is unclear. You can see here the spectra, just some examples of famous pulses, and you can see the distribution of energy. Again, you should add some actually points here because there are more observations, even from ground telescope, Chernyakhov telescopes. Veritas, for example, they observe now up to well above GeV. And they see that the spectrum actually extends to high energies. Now, so what do we have here? We have a rotating neutron star, basically rotating sphere with magnetic field. On large scales, it should be dipole field because dipole component dominates. It has the slowest decay with distance from the star. And it has some spin rate. Okay, so angular momentum vector and magnetic moment vector. That's it. The two parameters of the problem. And what we observe is there's coherent radio emission from this object, X-ray broadband emission through X-rays up to the gamma rays. But we also see a lot of electron positron plasma ejected by the system. Like in the Crab Nebula, for example, we see that huge number of pairs are supplied by the central source, and they produce synchron emission. Sometimes to use this parameter multiplicity, it's the normalized plasma density when you try to estimate using the simplest model of what using basically electric currents, which I'll talk about later, that circulate in the Newton's star magnetosphere. You divide this electric current by electron charge, you get the number of particles that you expect to be sort of going through the magnetosphere. And what you need to have to be ejected in the Crab Nebula is 10 to the 5, 10 to the 6 times larger than this basic number, what they call Goldreich-Julian charge current. So a lot of very efficient machine in producing and injecting electron positron pairs. Okay, so that's the basic background. This problem, well, okay. Like I said, very simple problem. Supposed to omega and magnetic moment mu, or maybe misaligned, supposed to be paradise for a theorist because you're supposed to solve such problems from first principles. What happened to be for 4 decades is not ultimate paradise, but ultimate torture, because most of the time, well, this is something that we learned, of course, in these 4 decades, but the basic questions were still not answered, like how you produce gamma rays, how particles and where they're accelerated, what controls the multiplicity, etc. I will give you first, before showing the recent developments, I will briefly guide you through the history, okay, starting from the end of 60s, right after the discovery of pulsars in 1967. The first thing you can do that was done in the 60s is to say, okay, I have this magnetic moment. If I have misalignment, I should have magnetodipole radiation. It's just like the dipole radiation. I have this mu double dot, second derivative of mu, that produces. I'm sure you're familiar with the dipole formula, but a similar formula for magnetodipole radiation. This is how much this object should be losing, how much energy it should be losing per unit time. It's proportional to omega to the 4th, so omega squared for 2 dots, time derivatives, and squared. And it should scale with mu squared, right? So basically we have mu squared times omega to the 4th divided by c cubed. Very nice formula. The energy has to come from the rotational energy stored on the side. There is no other source of energy in this problem. Okay? If magnetic moment is fixed, it's magnetic energy is sort of fixed. So you tap into rotational energy only. So if you are given, you know approximately what's the moment of inertia of a sphere of radius 10 kilometer and mass 1.4 solar masses. This moment of inertia is 10 to the 45 in CGS units. Multiply by omega squared over 2. This is the kinetic energy. So this is the simple formula that observers have been using for years, trying to estimate, for example, mu. Right? If you measure, you know I, if you measure omega dot, the spin down rate, the rate of change of this quantity, you can estimate mu or surface B also. All right, but this picture cannot be, of course, right. For a simple reason that was immediately, very quickly figured out, also in the end of the 60s. If you assume really vacuum around the star, this is what this formula assumes. It's a vacuum, magnetodipole radiation, assuming vacuum here. You can calculate the electromagnetic field in this vacuum wave that goes from the star. And what you find, there is an electric field component along the magnetic field. So if you place there a seed particle, it's going to be accelerated by this electric field along the magnetic field lines. You cannot move across the field lines because it's so strong field. All the particles are basically kept in the zero Landau state. If you excite to give it perpendicular momentum, the particle relaxes very quickly to the motion exclusively parallel to the field. But if you have electric field parallel to B, it's going to accelerate the particles like beads on a wire. Okay, you can quickly estimate. You can imagine. You can find. You have the electromagnetic solution, of course, this vacuum solution. You can place a test particle and follow its acceleration, and you will find it will reach huge Lorentz factors. Let's say 10 to the 11th, and it will start to produce secondary electron poised from plasma. It's a two-step process. It will first produce gamma emission, let's say through curvature radiation. The particle has acceleration because it moves along the curved field lines. Its speed is basically the speed of light, but it's curved. So it produces dipole radiation, which happens to be in the gamma ray band. If you have Lorentz factors of these particles above 1 million, in this case you will be well above 1 million. And then these gamma rays cannot actually survive in the strong magnetic field of a Newton star. They convert to pairs. So you have immediately a mechanism. If you start with vacuum solution, you find it's not self-consistent. Put a seed particle, develop electron Poisson cascade. And then you might conclude that what should be happening in reality is that instead of vacuum, you have a very efficient way of filling the magnetosphere with plasma. And okay, then you can start with the opposite assumption, that it's a dipole, rotating dipole, now immersed in plasma. Okay? And the job of this plasma is to screen the electric field parallel to B. Because this is what plasma should be doing. It always polarizes to screen electric field. It's very easy to produce secondary particles, so it seems very natural to assume that. And this is what people call force-free model of magnetospheres. Once you made this assumption, actually, you can forget about the plasma, because now we can talk just about electric and magnetic fields. If you assume that E dot B is 0, if you have this force-free assumption, then you can actually close the set of equations for electromagnetic field without thinking what the plasma is doing. You just use, you can actually calculate what J and rho, the sources in the Maxwell equation, should be to satisfy this force-free equation. And you assume that the plasma adjusts in this way. Okay? All right, so this is what was done next, 1969 by Goldberg-Julian classical paper. For the aligned rotator case, that is when omega is aligned or anti-aligned with mu, then you have this plasma that has to be co-rotating with the star. If you place a particle, it's going to do E cross B drift, what they call. But anyway, plasma basically follows the rotation from the star. It's communicated to the magnetosphere. And what you find in these force-free solutions, that you have to, well, basically you find it from here. You have electric field. What this line gives you is that electric field is 0 in the co-rotating frame of the star, right? This is how you transform electric field from the lab frame to the co-rotating frame, the standard transformation. And if you if you have a good conductor here, this electric field has to be 0. In this way, you can find the electric field from here. You know the rotation velocity. You know B, let's say proximity dipole field. And then you can find div E, divergence of electric field, which gives you charge density, which is called Goldreich-Julin charge density. It's the density that has to be sustained, charge density that has to be sustained by this magnetosphere if you want electric fields to be screened. Okay, very simple, very nice model. Now this is a sketch from Goldreich-Julin paper. What you also find in this, once you look at this model, you find that there are two types of field lines in this problem. The closed zone that goes up to the light cylinder. The light cylinder is the distance where the co-rotation speed with the star is equal to the speed of light, so you cannot co-rotate outside the light cylinder. So the field lines that go up to the light cylinder, they are going to be open. And there should be some outflow of plasma along these field lines. This is the basic conclusion of Goldreich-Julin. Even more important conclusion is that there must be electric current circulating through the magnetosphere. And I'm not going to explain how it's derived, but it's actually pretty straightforward. Electric current, which, so there is toroidal field here sustained by the poloidal electric current flowing here. You can think of this electric current to first approximation, this current density, as this Goldreich-Julin charge density that I mentioned before, the co-rotational charge density, times the speed of light. And if you integrate it over area, you get this characteristic current. Anyway, it scales as rotational velocity squared times the magnetic moment divided by c. There is a circulating current. And also, this current implies a spin-down power. That is, the best way to think about it probably is like this. You have current, you have toroidal magnetic field by Stokes' theorem. So you have the phi component of the field and the radial component of the field. So the product of b phi br is the magnetic stress that is applied to the surface. And this is how you extract energy from the star. The rotational energy flows from the star in the form of this Poynting flux along the magnetic field lines all the way to through the light cylinder and then to infinity. And that's the power that, that we see in the Crab Nebula, for example. This is this Poynting flux. All right, technically, well, this was done back in the 60s. And that was a qualitative picture that they proposed. But there was no solution, actually, for these force-free equations. If you write in a relativistic way, in covariant way, this would be electromagnetic tensor, F mu nu, right? This is full vector, full current. And the force-free equations read just this. It's very simple in covariant form. And you can try to solve these equations. And not until 1999. So for 3 decades, the equations remained unsolved. So finally, they were solved by Kantopoulos et al., and then a few other people. Timokin worked on that, and then Spitkovsky did numerical simulation for inclined rotators. Basically, the solution sort of confirmed that picture. I will show you the solution. This is the current density. Okay, these are two. This panel shows the current density. The color shows current density, and here you see charge density, divergence of electric field. It's a funny structure. So it is poloidal plane, okay? Meaning you don't see the phi direction here. It's meridional plane.
And this is for an aligned rotator.
This is for an aligned rotator, yes. What you see here, there is a one sign of current flowing, let's say, this way, and there is a return current that flows in the opposite way, opposite colors. The return current is concentrated near the current sheet. It's a funny structure if you think of it. The charge density is even more strange. You have charge density of one sign concentrated in this thin layer, and there is this closed zone which has net positive charge. So this is what you find by solving this force-free without thinking about what the plasma is doing. Plasma is supposed to adjust to respect this force-free solution. All right. Now, the last part of history is here. So next, you have to ask the question. It's very easy to understand why you have to ask this question. Of course, neither vacuum nor force-free models can be correct. because they don't accelerate particles. I mean, there is no plasma. In vacuum, there is no plasma by definition. In force-free, there is plasma, but there is no acceleration of particles. So you cannot possibly explain by these models the activity that you observe. This is a fundamental question that you have to address. So you have to change the framework in which you describe this problem. And people worked hard on this problem for 4 decades. I already mentioned that you can easily produce plasma. So people were thinking about deviations from this force-free, that is gaps, where strong electric fields actually exist, and where you can expect a pair discharge to be sustained, and that would be responsible for the activity that you see, creating pair plasma. The discharge can operate in 2 ways, 2 basic ways for the discharge to work. In both cases, you invoke particle acceleration and emission of gamma rays, and then these gamma rays can convert to electron-positron pairs in 2 ways. One is just conversion of the field. You can't convert a gamma ray into pair in vacuum because you cannot satisfy energy conservation and momentum conservation. But then you have background field that can take part of the momentum. This process is allowed. And actually, it has very high rate when the magnetic fields are strong, 10 to the 12 Gauss, let's say, typical for pulsars. The other way is to have this gamma ray collide with another photon, and then 2 photons form a pair. Okay? The second way is efficient, obviously, when you have targets for these collisions. And you have these targets only in young pulses where radiation density is significant up to the light cylinder. So you have good targets for photon-photon collisions. For Crab, for example, young pulsar, fast rotating, the light cylinder is closed. So density of radiation, synchron photons that come from that region is high. So if you produce a gamma ray is thinking, there are many targets, let me convert to a pair. Okay? If you have an older pulsar with 1 second period, if you produce gamma rays at the light cylinder, they just escape. They have no chance to convert to pairs. They're 2 qualitatively different regimes. It's a very important point, it turns out. It was not appreciated, actually, until very recent developments. Okay, there was a lot of discussion, and it's here, I remember, 10 years ago, and I don't know how many talks you still hear about it. People discuss possible location of gaps. There are 3 types of gaps. There's pole cap gap, there's slot gap, and there is outer gap. I don't want to plunge into that. Like you would hear a talk separately on just outer gap, for example, or sometimes combine pole cap and slot gap. I'm going to omit that. I would say this, unknown, because, and you'll see why actually in a second. I don't believe all these models, and actually the goal is to answer the question where the gap should be. So let me formulate this a pulsar puzzle. There are 4 basic questions that you're supposed to answer as a physicist when you approach this problem. Where the plasma is created in the magnetosphere, how much plasma is ejected in the wind, okay, in the Crab Nebula wind, for example, where and how are gamma rays emitted, and another fundamental question, again, not answered yet, how are coherent radio waves produced, okay? I think that to escape this 4-decade torture, it's now becoming clear the right path to escape is to do numerical simulation from first principles. And I will see some, you will see some success already on this way, which is very recent. Okay. Now, how do we formulate this problem? You want to solve it from first principles, no cooking. Okay. So if you see somewhere, if you have a question about how the problem, don't assume that I adjust anything. You stop and ask me, all right? Ask question. I don't want to spend too much time on the technical part, but if you have a question, please do ask me. So the way the problem is formulated, I'll just briefly guide you through the formulation. Again, you have, just look at the line rotator case. You have, with dipole field, you have this dipole field and you have rotation. The best way, I think, to formulate this numerical experiment is to start with the simplest state when there is no rotation and the dipole field in vacuum, this self-consistent state. and then give the star some rotation, increase it, and then saturate rotation rate. This is a direct experiment, well, numerical experiment, that you hope would show what happens in the steady state. Because otherwise you have to decide what would be the initial conditions, and I think it's a very good way to but in the end it turns out the results actually do not depend on the choice of initial conditions, I think. All right, now what happens when you spin up the star? You start with vacuum, remember? So what's happening in this like unipolar inductor is inducing electric fields, this V cross B fields. There is electric field component, which I mentioned before, along the magnetic field lines, and it's going to lift some particles from the surface. Okay? You don't need to assume anything how you supply this plasma. That's a key point, because in some simulations, actually, you do this by hand. Actually, you don't need to assume that. If you start to oversupply the plasma, the electric field will change sign and will push the particles back. If your electric field is too slow, you will start to increase the...
So you sort of a thin layer of protons and electrons on the outside?
Exactly. You make the particles available. There is an ocean of particles, like it should be in reality.
Right.
And then the electric field self-regulates itself in the supply of particles. It's a self-consistent problem.
The C gets charged, basically, because you're taking out more electrons, say, than protons?
No. No. So if you... So, okay, yes, it depends on what you assume, but in reality, no. In the simulation, no. If protons cannot escape because there's big binding energy, in that case, you do form a charge, a surface charge on the star. But in reality, for pulses, it's not the case. The binding energy has been calculated. Early models, Ruderman in the 60s showed that binding energy, or found that estimated the binding energy, and thought, oh, ions are bound. And that's why they talked about anti-ion rotator, where protons are kept on the star. And then you have the surface charge. But later, work by few people, Jones, for example, and most recently, Midden and Lai, they calculated the binding energy more carefully. And the conclusion is that for most pulses, you easily lift ions. So it's a temperature, thermal emission is strong enough. So the work function is, the binding energy is basically zero, you could say, for most pulses. The only violation of this easy supply of particles would happen when you have very cold and very strongly magnetized star. Not many of those. If you have magnetars, actually, they are usually hot. All right, so, and if you have these particles available with zero work function, then there's no surface charges are tolerated. Just lift them, okay? So the inner boundary condition, you cannot play with it. It's just given, all right?
Doesn't matter what density you sprinkle onto the...
Doesn't matter. You don't want to do something crazy, so your numerical scheme would break. But so you want to find this physical regime when you have... inside the star, it's going to be equal to Goldreich-Julian. Because it's the star is rigid, the field is fixed, Goldreich-Julian is fixed. Yeah. All right, so this is one important thing. So the particles are extracted from the star. Of course, in numerical simulation, you also have the outer boundary. You just let the plasma escape there, and the waves. Just minimize any whatever reflection you might see numerically. It's possible to do. Now, in this approach, it's first principle experiment. The best way to do that is to think of this plasma as collection of individual particles. Okay, so you follow, let's say, 100 million particles in the simulation. Whatever particles you have lifted from the star, whatever particles have been created, you follow how they accelerated, they produce gamma rays, and then they create pairs. And you calculate the electric currents that they produce. And then they use this electric current as the source term in the Maxwell equation that you need if you want to solve for the self-consistent electromagnetic field. So it's a self-consistent coupled system. When you solve for particle motion, just accelerated by fields, and you have two equations that tell you how the electromagnetic field evolves. And you have here this J. So this J is calculated self-consistently because you know what particles are doing. You know P for each particle, you know J.
Presumably you can't model as many as there would really be in the magnetosphere. You have to somehow
yes, so that's what...
take a different charge.
That's right. You increase the charge, basically, effectively. But of course, you can follow how this... you should stay far from the case where if you think it's dangerous. I mean, too few particles, obviously, you cannot reproduce the system. But 10 million or 100 million is certainly more than enough in that sense. All right. So another important part is you need to do the radiative transfer, which means that you need to follow how photons are emitted and then how these photons convert to pairs. So Alex Chen at Columbia, who's a PhD student, developed a new code for this problem from scratch because the existing codes are not perfect they're not designed actually for this problem. For example, Tristan MP initially was designed mostly for shocks, and therefore it's Cartesian grid code. And here, obviously, you need to use spherical geometry. It's better because you can resolve the star. So it's a particle in cell code, which is on a curvilinear grid. So fields are evolved on a grid, of course. That's why it's called particle in cell. Each grid cell, you identify the electric current in each grid cell, and then follow the evolution there. Of course, it's relativistic code. It has to be relativistic. The particles gain huge momentum. And then another reason to develop a new code was, it's actually the first code and the only one existing, I think, where we follow photon production and the radiative transfer in the magnetosphere. That is, when you have an accelerated particle, we calculate its trajectory, and then we know the dipole emission from this particle, which is both curvature radiation and synchrotron radiation. So you can calculate its emission from first principles, right? So it's at high energies. At low energies, you also follow all everything self-consistently because it's a plasma simulation. So you resolve the skin depth or the Debye depth. So it's an extremely interesting problem when you combine both high energy and low energy aspects. The only way to do that is to bring the scales, which are in reality hugely separated, like Debye length versus the biggest scale is here, the light cylinder. There's a huge, many orders of magnitude. So you compress this in these scales, but of course you preserve the hierarchy of scales. So you still need high resolution in the simulation so you can separate the scales very well. And the way to check if your separation is good enough is to double the size of the simulation to see if you have approached, if your results are saturated. Okay? So I hope that's enough for the technical setup. You can ask me questions if you like about that. Let me show the results. Now, again, to emphasize that there are no assumptions about where to create plasma, not to create. If you see a particle in a given field and it has this Lorentz factor and it is producing the gamma rays, well, let's follow this gamma rays and see if they convert to pairs. Okay, so you don't need any assumptions there. It's a first principle simulation. Given that initially the system knows nothing about, well, the plasma initially, so you increase the spin and you hope that the magnetic field will change in an interesting way, but you would expect a smooth solution. Okay, you might generate some currents. Let me show what's happening in this simulation. This figure shows, okay, green, I hope you can see the green curves, show the poloidal field lines. It's just magnetic field lines, dipole field. We don't plot the field lines here, just not to be too cluttered. And the color will show electric current. If it's red, it's positive. If it's blue, it's negative. Okay, initially no plasma, no current. It's black. Initially no rotation. Very quickly, in 10 light crossing times of the star, the time is shown there, it will be running, you stop spinning up the star, and then you live with steady rotation, and you look for your quasi-steady state. Okay, so let's go. You see two signs of currents are extracted. It's actually the null line. Rogel-Rag-Julian changes sign, for those of you who knows, so it's not surprising. Anyway, so there are there are two opposite currents extracted. Initially, they have similar thickness, and later, this opposite current, the return current, is becoming a very thin current sheet. And remarkably, the system evolves to what you have seen in the force-free, not exactly, but qualitatively close. So this first principle experiment actually does verify that pair creation self-organizes in such a way that it operates where it needs to operate. That is, a force-free state where electric field screened, or almost screened, Once the current to flow and the plasma to flow mostly in a thin layer, the pair creation, which could be happening here or here, chooses to happen in this layer. It's an amazing example of nonlinear physics, which actually, well, sort of verifies in some way the expectations, but not quite, as I will tell you soon. There are many interesting details that you can study here. You see the gyration. Particles gyrate.
Is that sort of what John Aarons was always hoping would explain the waves that you see in the crab?
Wisps, no, this is different scale. Yeah, wisps come from the wind that out in fracts. Yeah, this is the light cylinder. Light cylinder here, you can barely see this line. This is the light cylinder. In this case, it's at 6 stellar radii. Okay, two opposite currents. They are conducted by qualitatively different mechanisms. Current here involves no pair creation, and it's conducted by plasma extracted from the star, electrons. In this case, it's negative current. The opposite current requires pair creation. So all pairs basically are created here around this red region.
So in both poles, you're having electrons flowing out, or am I reading this wrong?
Here, electrons are flowing out.
Yeah.
And here you have more complicated picture. Oh yeah, this is the, you see, okay, this is the sort of symmetric, yeah. Electrons go that way, yeah. You should actually, you might expect it because Rogel-Rag-Julian has the same sign here and here. Okay, this is the charge density.
Right, and this is for a neutron star, where it is aligned. So if you enter align, it does not matter.
It does matter in the following sense. In this simulation, we have ions and electrons. They have different mass.
Right.
So anti-aligned case is not the same.
Right.
It's not the same, but qualitatively, qualitatively is similar. If you like, I can go into details, but I think I better move on. Yeah. This is the charge. If you remember this force-free picture, there is this current sheet, negatively charged, and it's positively charged outside. It's also remarkable. And there is this closed zone, and there is this neutral line. Anyway, so what are the main things that you find from this? The main thing is, first now we know where the gap is forming, at least for axisymmetric case. The gap is forming along the current sheet. And the mechanism for gap formation is none of those that have been discussed before. It's not the outer gap, what they call, not the slot gap. It would be good to call it slot gap because it has a form of a slot. Maybe it should be called a slit gap or something. But it's not a polar cap gap. The mechanism for creating electric field, unscreened electric field, the best way to think about it this way. You start at the situation when you have no electric field. All electric fields are screened, that is, you have force-free configuration. And you ask the question, where is the easiest to break this configuration? Where is the most difficult to supply the plasma that would sustain them? When you look at the charge density distribution, you immediately understand that actually the charge density here is very high. And in the idealized force-free models, actually it's infinitely high. So that's the place where it's very easy to have charge starvation relative to the force-free configuration. And Rogel-Rag-Julian has nothing to do with that, because Rogel-Rag-Julian here is actually changing sign across this line. You would have here the positive charge, and the actual force-free solution does not follow this gravitational density. It has this spike. So naturally, the system finds it difficult to replenish this plasma, to sustain this high charge density, and there is a gap that develops there that continually tries to supply the plasma and continually tries to fill this gap with plasma. So that's the place where the particles are accelerated. And surprisingly, I don't know any paper in these 4 decades that would actually point out to this mechanism and say that's the mechanism how gap is formed. And that explains why the gap is here. Now, why there is no gap here, I think actually I explained it in 2008. There was a paper that made a very simple argument that there should be enough plasma flowing from the polar cap to screen the electric field. Anyway, basically here the current that the magnetosphere wants to have is not too strong, so it's easy to supply it by particles just extracted from the pole cap. No need for pair creation. And one more figure here. Well, actually two more. That's again the magnetosphere, the field lines. This shows the ion energy. The color is the ion energy in units of mc squared. You can see where particles are accelerated. Basically, this ion energy is like a marker for the voltage, because ions don't lose much energy. They are just accelerated, unlike electrons that experience radiation reaction effect, so they lose energy. So when you look at ions, you see where you pick up the voltage. You see beautifully how these high energy ions accelerated in this slit gap or whatever, how they eject it and then gyrate and form this nice outflow. Basically, you can think of it as a nozzle formed by the magnetic field lines and collimating the plasma outflow. There are two opposite streams that start to gyrate like this. So they cancel their opposite momenta, okay, and they form this net outflow. And this figure shows the ratio of plasma energy to magnetic energy. So everywhere magnetic energy dominates, as you should expect, this is the force free, except for this collimated outflow region where plasma dominates. So this is an outflow collimated by this magnetic energy. And one more thing you want to know, I guess, is where you produce the gamma rays. Since we follow the transfer and production of gamma rays, we can just, like here, show each emission event in the simulation. We can show the location of gamma ray emission, and also the color show here is the angle of this gamma ray with respect to the vertical axis, which gives you, and then you can translate it to the light curve if you like.
And these are gamma rays that escape? Or?
That is, actually here, no. But they have, yeah, here are all gamma rays. Many of them escape, some of them don't. All right, so the bottom line, a lot of them there, yes, because here we have reconnection, energy is still given to the plasma. So the basic conclusion here is very simple. Gamma rays are produced in this Y-shaped current sheet. Okay, yeah?
In all the other pictures you've shown, it looks symmetric about z equals 0. This one doesn't look symmetric.
It is not exactly symmetric. Simulation does not have any symmetry built in. So actually, this is somewhat time dependent. This gap here breathes. So you can see here, and it breathes differently because it's sort of, there is some random element there. I can explain even why it breathes. Actually, in the anti-line rotator case, it breathes more. In the Y point, it breathes a little bit around the light cylinder. It depends on the details of how you, you can understand it. I better move on to the next thing I wanted to talk about. I don't have much time left, right? But I'm happy to talk more about this. Let me just show one more plot. Now, note that all these results that I have shown so far are for the case where you can easily produce pairs all the way to the light cylinder, like the Crab case, where you have these photon-photon collisions, okay? Producing pairs. Now, for many pulses, this channel is not available. And the only place where you can produce pairs is close to the star, let's say a few stellar radii, where the magnetic field is strong enough to block high-energy photons from escaping. Now, if you run the same thing, the same simulation, but now switch off pair creation here, just say no pair creation, but here keep pair creation up to.
In your initial simulation, you assume there is some thermal? Or
I assume that there is target density, and when we do Monte Carlo, we draw a free path from a distribution, which is supposed to model target field. This target field, there is no reason to go into much detail because this target radiation for gamma-gamma reaction varies from pulsar to pulsar. So you choose just one, because here we're talking about basic things actually.
Yeah. To see the case where it's easy to do it and one where it's difficult.
Right. When you want to know how the machine works, you need to look at two cases. One, there is target density. Two, there's no targets. And then you can do this in much more detail. The simulation can be done in much more detail, but I think it should be done individually. Like you take the Crab pulsar, do it for the crowd, because from observations you have an idea what radiation density is, but this have not been done yet. Well, still thinking about principal questions here. Okay, so if you switch off the channel, do the same thing, then the result, and this is a big surprise actually, this is what no one would anticipate. Well, we sort of anticipated that, but it took us to time, a year or so, to actually see this in the simulations. That's, in this case, you see the final state. It's not a movie. I have a movie if you like, if you're interested after the talk. The final state is such that the few lines are dipole, quasi-dipole. And there is just plasma sitting there statically. And the current is some weak current flowing there, but it's very weak. So it's dead. Axisymmetric pulses, a line rotator, has no activity, almost no spin down power, if there is no pericreation at the light cylinder. If you rely only in terms of pericreation only in the region near the star, before people would think, well, I have huge Lorentz factors there. I can inject a lot of plasma and it would flow out and screen the electric fields. I should be force free. So that's wrong. It doesn't find a self-consistent state. Instead, it relaxes to what they call electrosphere. Two opposite charges just trapped. All right, there are a few groups that work on this now. So one with 3 different codes. So besides, so Alex has his own code, and then based on Tristan MP, Anatoly Spitkovsky and his group, in particular Sasha Filipov, and yes. So I'm also working on this problem. They recently published a month ago a preprint on Archive as for PH, where they confirm this result and basically find same structure for the magnetosphere in the 2 cases. Now there is also Benoit Chiruti code, which is different. He looked at slightly different problem. He focused mostly on what's happening in the equatorial sheet, but there's also a very nice simulation showing how energy is dissipated in the equatorial current sheet outside the Y point, because he doesn't have pericreation, but he follows the physics there very carefully. And this is the a couple of figures from Filipov et al. Paper on Archive. 2 cases. Now, the big difference here is that this is now a line case. This is axisymmetric case. And, sorry, this is a line case, and this is inclined case. So now the next goal is the charge. The current flow. J parallel means current measured along the magnetic field. So the obvious next development that should be done is the careful study of 3D configuration with inclined rotator. And I think still, and this is what they see, and it's what I think should be happening too, the gamma ray emission mostly comes from this Y-shaped current sheet, but now it's inclined and it's like wobbling like that. But also when you have, on your,
90 degrees inclined?
This is 60 degrees, I think. When you have 90 degrees.
From the rotation axis or so.
Yeah, I think so. From above. Yeah, you should ask them about it, and you can read their paper. Yeah, I have no good explanation yet for what's happening in 3D. I'm a little bit surprised with some of their results, especially for low inclination. They find that when you have inclination of 40 degrees or less, they basically find the same solution as we find for newly aligned case. I would think that there should be some pericreation at the pole cap, even at smaller than 40 degrees. But that's something, we'll have a small workshop soon, and then we'll discuss these details. Anyway, so this is going to be even bigger developments, I think, in the future when the 3D models are run and fully inclined rotators with higher resolution, and we understand better what's happening. 3D, of course, is much more challenging. They have Cartesian grid, so it's easier for them. It's natural for them to focus more on 3D than axisymmetric case, because how do you do axisymmetric case in Cartesian grid? You have to still have to do it in 3D, right? Anyway, so there is another recent work by Beloborodov at Berkeley, also uses a modified version of Tristan MP code. He's also working on implementing pair creation self-consistently. So the big development is that now we have peak simulations with pair discharge. So far, radiative transfer is only done by our code, but I think in the future, I'm sure there will be more simulations like that. So the future, I see two big developments in the future in this field. I spend most of my time on this part anyway. Inclined rotators, obviously, because you want to see the light curves for gamma rays and compare it with observations. A line rotator does not pulsate, right? So even if you have good models, you still have to, it's not interesting for observed pulsars. And another big question that has not been approached yet, but all the information should be contained in these simulations because they resolve all the plasma processes. It's how coherent radiation is produced. What is the emission mechanism? And now I have 5 minutes, I think, right? Yeah. For those of you who are interested in magnetars, all right, what can I do in 5 minutes? Magnetars are very strongly magnetized neutron stars. End of story. Now, okay, so magnetars are active stars that produce outbursts. They produce giant flares and also outbursts that might last a year or something. The basic reason of their activity is that the star is alive in the sense that its surface is moving in time. On a time scales much shorter than the age of the star. Sometimes weeks and maybe even faster if you associate the giant flare, which has duration. The main peak is a fraction of a second. If you think it comes from the instability in the crust, you would have to assume that somehow the surface moving in a fraction of seconds by a radian or something. So the basic picture is not very different from the sun to zero approximation. For 5-minute exposition, that certainly would be enough. You twist the fields, and you have electric currents flowing through the magnetosphere. And you can generate, well, solar flares, giant flares in this case. Now we have nice simulations for that. This is twisted snapshot of real careful simulation, force-free simulation, actually time-dependent, by Kyle Parfrey. This is the 3D picture of this. What happens if you start with dipole field and start to twist, that is, take the polar cap of the star and rotate it with respect to the rest of the star. This is simplest axisymmetric model of how you can deform the external magnetic field by moving part of the star. And then you see how you build up the twist. The color shows the ratio of B phi to B, which you also can see from the shape of the field lines. And then you see how the magnetosphere inflates. And then at some point it will become unstable, and it will produce a giant flare. And then it relaxes back, and you can see there's still some twist. And the process will repeat. So just one example. It's actually one significant development that we can now simulate and understand what's happening at least in axial symmetry with magnetic fields attached to evolving star. Okay, I'll skip all that, and yeah. Okay, you already talked about thermoplastic waves. Okay, that's good. So I'll just tell you one last piece of information. It's the recent development this year, actually, and a little bit last year. The mechanism of hard X-ray. This is a 10-year-old puzzle. It was discovered. Magnetars produce 2 peaks in the X-ray spectra: soft peak, keV peak, and 100 keV 1 MeV peak. The origin of this emission has been controversial, and there was no model that could be compared directly to observations, like from not simple enough, maybe with some parameters, maybe. So we've been thinking for quite a while about that. I think now we have a model which is simple and can be understood from first principles, and actually now it's fitted to the data, and it works beautifully. And I think it's, this in my mind, this part is basically done. I think we understand now how hard X-rays are produced by these twisted magnetospheres. And that's the basic picture for the theory, and then I'll show the fits and then I'll stop. Just one picture for the theory. What's happening here is electron-positron discharge near the star with high multiplicity ejects electron-positron fountain. And then as the plasma outflows, it upscatters photons and basically loses its energy to radiation. So of course this emission is collimated because it's a relativistic plasma which is decelerating. Eventually it comes to stop. It accumulates there, annihilates. But here it starts with very high Lorentz factors, 1,000 to 100. It doesn't really matter for the metal, as long as it's much higher than 10, certainly much higher than 10. So there are two zones here in this outflow if you want to understand the basic physics picture. One thing you need to know is that photons that are produced here, and they're produced through resonance scattering, by the way, but can't forget about this detail. You have gamma rays that cannot escape, so they turn into pairs. So what's happening in this region is that the outflow reprocesses its energy into next generations of pairs. Nothing escapes, like adiabatic outflow. And then there is a sharp boundary at the field of about 10 to the 13 Gauss, with good accuracy, at which you have the sharp transition to free escape of these gamma rays that are produced. And since you know the Lorentz factor, you can actually calculate how plasma is decelerating with distance from the star. It turns out this Lorentz factor is just decreasing proportional to the local magnetic field. One can show that, and I had more time, I could explain the simple physics behind that. Once you know the Lorentz factor of the outflow, and you know that it's emitting photons through resonance scattering, that is in its rest frame, it's producing photons equal to the Landau, an energy equal to the Landau energy, that's sufficient to calculate the spectrum that should be produced by this outflow, this fountain. So it's a very simple problem, in fact. And the spectrum is not surprising. It's what they call sometimes fast cooling, because effectively it's like fast cooling. Basically, you inject plasma, you let it cool, and it produces a spectrum with a slope of 1/2. There are other examples, fast cooling with not resonance scattering, like inverse Compton or synchrotron cooling, but it still would be the same slope. Now, the interesting thing here is not just the average spectrum, is that this average spectrum actually looks very different if you look at different angles at this object. Okay, this is spectrum in 4 pi. If you look at different angles, you see completely different spectra. They add up to this e to the 1/2. Now, how do you test this simple fountain model? Okay, you just take this fountain. It goes along the dipole field lines. This rotation axis. That's your main parameter. Okay, set it in rotation, and you look at this object along some line of sight. Two angles between magnetic field, magnetic dipole, and rotation axis, and line of sight. And try to fit the spectrum. Now, the good thing is that now we have the data, especially now when new star is working, and there are a few objects for which before was analyzed for XT and integral, where we have the phase-resolved X-ray spectra. And this is precisely what you need here. Now, let me show you the data, and then I'll stop. So these are the fits, okay? These are the two angles that I mentioned. This is the angle between magnetic axis, and this is the angle of the observer. Okay, I don't show the phase-resolved spectra because it would be too much. I just show the part of the fit for the phase average spectrum. But actually, the spectrum varies dramatically with phase. It changes its slope. I suspect even the peak may be changing, but the peak is actually high enough here. So when you take this and fit with this alpha and beta, this is what you find for 3 objects, okay, for which we have good data. Now there is actually a 4th one from new star. So what you find is that the model desperately fails for almost all angles. The green zone is where your whatever p-value, low p-value means big chi-square. Okay. So white here is good chi-square. What you see, the model is desperately fails almost everywhere. But there is this mountain, and okay, there is some, because it's axisymmetric, one can show that actually there's degeneracy. We cannot distinguish between replacing alpha with beta, okay? So there are 2 models that would fit. But if you forget about this symmetry, just look at this part. There is an island where the model fits perfectly, okay? And to me, it's the sign that the model is right. It does not only fit, it also tells you the parameters. It allows you to measure this alpha and beta. This is another example. We did it a little bit worse, but you can still see this peak. This is another beautiful example where it is in very narrow region in parameter space, where small region where the model fits. And so I think that's the right. So the bottom line here is that the hard X-ray peak that we see in magnetars in persistent emission is produced by this fountain of outflowing plasma through resonance scattering, and it goes up to MeV. And I should stop here. Yeah, thank you.
Any further questions?
Any example where you can show the phase result of this?
Well, yeah, I have it on my computer. I can show you later. Like, no, not on the top.
Because
Yeah.
well, at some level, maybe because it's the complexity, I would think that really proves the case. Like this kind of curve would be.
Okay. Yeah. While you're thinking about another question, I can show you that I certainly have the data for different phases, and not with curves.
No,
Yeah. Yeah, go ahead. If you give me 30 seconds, or I can, if I don't find it so quickly.
I'll show you afterwards.
Okay.
I want to hold everybody.
Okay. But so they're dramatically different at different phases. In some cases, we have 3 beams. In some cases, we have 5 phase beams. And the first work was by, the most impressive work actually was done back in 2008 on phase result spectra by Peter Den Hartog for a couple of objects. Yeah.
So, one last question. To get those fits, you're assuming some twist, right? Some current that you have caused by.
Yes. Okay. Right. So I said besides these 2 parameters, actually, there are a couple more. So there is this not the twist. It comes in combination. Basically, the power that flows in that, and the other parameter is the size of this the size of this fountain, because it could be very narrow, it could be broad, right? I mean, on the star, the polar cap that produces this outflow, and again, from these fits we can measure, sort of estimate the size, and we find that it occupies about 1% of the area of the star in the polar cap in this axisymmetric model.
Any more questions? All right, let's thank Andrei again.